Welcome back to the today's class. Today we will be seeing about description of AC wave in terms of peak value, average value and RMS value. First we will be discussing about root mean square value, which is RMS value. The effective RMS value of an alternating current is given by that steady current DC which when flowing through a given circuit for a given time produces the same amount of heat as produced by the alternating current, which when flowing through the same circuit for the same time is known as RMS value. So RMS value is very easy to understand. If you think about a DC circuit and a DC battery and a resistor is connected in the circuit, if a DC current is flowing through a resistance, so due to I square R loss, the resistance will be heated. Okay, consider we will heat the resistance or we will flow the current into the resistance for 1 hour. If the current is flown for 1 hour, then the resistance gets heated up to 80 degrees centigrade for 1 hour. So, in the same case, if we use alternating current or a AC voltage instead of battery to heat up the resistance, then the time required for the alternating current to heat up the resistance is not the same, because you know that the DC current is a steady wave whereas the alternating current is a sinusoidal wave. So because of the nature of the sinusoidal wave, it takes more time to heat up the resistance. Due to this phenomena, we will define these two values in respects of RMS value or root mean square value. Importance of root mean square value. In case of alternating quantities, the RMS values are used for specifying magnitude of alternating quantities, that is 230 volt, 110 volt, or the RMS value of an alternating current. If you consider the ratings of AC appliances, in the nameplate details of the appliances, they will be mentioning that it is 230 volt or 110 volt. So the appliances measured value or the appliances which is shown in the nameplate details is the RMS value. So if appliances is rated for a voltage rating, then the voltage rating is rated in RMS value. The ammeter and voltmeters record the RMS values of the current and voltage respectively. So if we use a ammeter or a voltmeter to record the current or voltage flowing in a circuit, then these two instruments will note the RMS value of the current and voltage which is flowing in the circuit. The heat produced due to alternating current is proportional to the square of RMS value of the current. So, if you use a resistance to heat up the circuit, or if you use a heater to heat up the water, then the heat produced in the resistance will be proportional to the square of the RMS value of the current. Derivation for root mean square value. So you see this is the figure of the alternating current, this one, which is I is equal to Im sin theta. So we know that RMS value is the square of the current. So if you get I square, Im square sin square theta, then the wave will be like this. Okay, here this wave is I square and this wave is I wave. Here in the waveform of current, and the square of the current is shown in the graph, and t is the time period which is measured in x-axis, and y you are having the current in amperes. So first you can see the current I is equal to Im sin theta. From here, from the graph, you can say the current I which is flowing through the circuit is Im sin theta. So the square of the current is nothing but I square. So we will get I square m sin square theta. Next, what we are going to do is to find the area of square curve over half cycle. So here is the square curve. We are going to find the area of this curve. To do this, what we need to do is we need to integrate the current for a time duration of half cycle 0 to pi. For a half cycle from 0 to pi, we are going to integrate the current value in square, I square d theta. So integration of 0 to pi, I square d theta. Now you will get the square curve or over the half cycle. What you are going to do is the average value of the square of the current over half cycle is average of curve over half cycle divided by length of base over half cycle. So the formula to find the RMS value of the current will be integration of 0 to pi I square d theta divided by pi. So this is the formula to find the RMS value of a sinusoidal waveform. So here 1 by pi is a constant, so you can take 1 by pi outside of integration, and you are integrating for 0 to pi I square d theta. And here you know I square is Im square sine square theta d theta. So 1 by pi integration of 0 to pi Im square sine square d theta. Okay, next what you're going to do is here Im square is a constant, so you can remove Im square outside. So after Im square by pi, we will be getting 0 to pi integration of sine square theta d theta. So we can apply the formula for sine square theta, which is nothing but 1 minus cos 2 theta divided by 2 into d theta. So after applying the formula, you can integrate 1 minus cos 2 theta by 2 d theta for a value of 0 to pi. While integrating 1 with the d theta, we will get 0. After that, while we integrate cos 2 theta divided by 2, we will get sin 2 theta divided by 2. Okay. For this, we need to apply the ranges from 0 to pi. So we will get sine 2 pi by 2 minus sine 2 into 0 by 2. So we will get sine 0 will be 0 and sine pi will be pi. So what we get here is Im square divided by 2 pi into pi. So we can cancel these two terms, and you will get Im square by 2. Here is the term. So the RMS value of the current is, so we need to square root the average of the square of current. So what we need to do here is we need to find IRMS equal to square root of Im square divided by 2, which will be equivalent to Im by root 2. So we can get a value of 0.707 Im, whereas the same value will be given for voltage also. We have used a current wave of a sinusoidal waveform to find the root mean square value. If we use a voltage wave, we will get Vrms is equal to 0.707 Vm. The same value will be present, but instead of current RMS value, we need to represent the voltage RMS value. And here for current peak, Im is the maximum peak current. Here instead of maximum peak current, we need to represent maximum peak voltage Vm. Definition of average value. The average value of an alternating quantity is defined as that value which is obtained by averaging all the instantaneous values over a half cycle. For a sinusoidal waveform, the average value of a complete cycle will be 0. Importance of average value. So, the average values are used for the applications like battery charging. The charge transferred in capacitor circuit is measured in terms of average value. The average value of voltage and currents plays an important role in analysis of the rectifier circuit. The average value is indicated by DC ammeter and voltmeters. The average value of a purely sinusoidal waveform is always 0. So, if you need to find the average value of a sine wave for a complete cycle, then you know that in a full cycle of a sinusoidal wave, there will be a positive peak as well as a negative peak. So, if you average all the instantaneous values from the positive peak to the till end of the negative peak, then you will get a zero value. So, it should not be done. So, to find the average value of alternating quantity, only half cycle should be used. Derivation of average value. Here, this is the sinusoidal waveform of a current wave. Here in x-axis time is present and in y-axis the current is present. Now, consider the sinusoidal varying current I is equal to Im sin theta, same as the previous case. Now we know that the formula to find the average value IAV is equal to area under curve for half cycle divided by length of base over half cycle. So you need to find the area of the curve for the half cycle from 0 to pi. You need to find the area of this cycle. To find this thing, we need to do integration. So to do integration, the lower limit is 0 and the upper limit is pi, and what we are going to integrate is I d theta for a length of 0 to pi. So I is equal to integration of 0 to pi I d theta divided by phi. To find average value, this is the formula. So now you can substitute the I value, which is nothing but Im sin theta. Here Im represents the maximum peak value of the sinusoidal waveform. Here 1 by pi 0 to pi I d theta. Now you have to substitute I is equal to Im sin theta d theta. So 1 by pi integration of 0 to pi Im sin theta d theta will be present. Here Im is a constant, so you can take out Im. So you will get Im by pi integration of 0 to pi sin theta. So integrating sin theta, you will get a minus cos theta. We will be applying Im by pi minus cos theta 0 to pi. Now you can apply the limits 0 and pi in cos theta. So Im by pi minus cos pi plus cos 0. So while doing this, you will get a value of 2. So how to here is cos pi minus of cos pi is 1 and cos 0 is also 1. So what you having is 1 plus 1, you get 2. So Im by pi into 2. So you will get a maximum value, that is the average value of 2 Im by pi. So the average value is 2 Im by pi. For current, we can, what you can do is 2 by pi. You can make this constant to a single value. So I average is equal to 0.637 Im. And for voltage curve also, for voltage also, V average is equal to 0.637 Vm. We have used the alternating current waveform to find this average value. If you use a voltage waveform instead of current waveform, the only the average voltage and the maximum voltage will need to be changed. The other things, the derivation of 0.637 remains the same for both current and voltage. Form factor. The form factor of an alternating quantity is defined as the ratio of R.M.S value of the average value. So we need to divide R.M.S value divided by average value to find the form factor. So form factor is denoted by a symbol of Kf. So we know that the R.M.S value is 0.7071 Im and the average value is 0.6371 Im. So while dividing these two things, you will get a form factor for a pure sinusoidal waveform is 1.111. Similarly, we can find the crest or peak factor. To find the peak factor of an alternating quantity is defined as the ratio of maximum value to the RMS value. Peak factor is denoted by symbol Kp. Peak factor is equal to maximum value divided by RMS value. We know that maximum value is Im and the RMS value is 0.707 Im. So we can simplify this that peak factor will be equivalent to 1.414. Thank you.